name is Burcin Nalinci. I'm the lead R&D engineer at Zahner. And today's talk is titled Innovation in Four Dimensions, from Tacit Craft to Computational Knowledge. If you're not familiar with Zahner, we're a 125-year-old company, so that's 1897, located in Kansas City, Missouri. And we specialize in architectural sheet metal fabrication and installation at many scales. Over the decades, we've been part of many iconic and oftentimes uniquely challenging projects. And so I'm going to scroll through some of those examples and talk a little bit more about our kind of story. Our legacy is built on a culture of innovation, developing new technologies, passing down the generational knowledge of craft, and a desire to explore the unknown, often in collaboration with architects and partners that want to push the boundaries. When the right tools didn't exist, we built them, and we applied them in ways that reshaped architecture, turning sheet metal into complex geometry, pioneering new methods, and scaling custom finishes. And so by the 1990s, Zahner was among the first to link CNC machines to architectural models, most famously with Experience Music Project, and that was a turning point. Digital fabrication and computation merged, complex geometry became real in metal. This is our lineage. From union craft to new technologies, a culture built to innovate. And at the heart of it is something harder to define, but impossible to miss: the tacit craft carried in the hands of our people. Tacit craft is the unspoken, experience-based know-how, the kind that we cannot capture in data or manuals alone. An example of that is, for example, a welder knowing by feel when a seam gets too hot and adjusting speed or angle to kind of mitigate that. Or an installer adjusting panels on site, knowing when to nudge, flex, or ease a piece into place without damaging the surface. Got ahead of myself. Back. So this knowledge carried in the hands of our people defines who we are. It reminds us that the finishing touches belong to craftspeople, the difference between generational buildings and temporary ones. Our patented sheet metal seaming machine in the 1930s symbolized necessity driving innovation, but it was never about the tools alone. It was about how we applied them. And that kind of mindset has set decades of innovation in geometry, process, software, and machines. And it continues in R&D today. There we go. So alongside many other contributors, this is kind of the core R&D team, people who get to play, experiment, sometimes break things on the way to building something new. And our work is based on kind of this four dimensions, kind of the title suggests there. So hardware and robotics, software and computation, material innovation, and life cycle knowledge. These are not silos. Instead, they form systems, machines that extend the hand, software that connect people in place, material that evolve, and the knowledge that grow with every project we work on. So I'm going to scroll through some of the R&D examples here. We'll start in the shop with a project where union craft meets automation with robot-assisted welding. So with every challenging project we get, robots kind of give us that flexibility. So we love robots. And also our history in union craft, we've been developing these robot-assisted workflows to combine the precision and repeatability of the robot and also the intuition of the craftspeople. And this is all towards empowering, the craftsmen. So where this process had great impact on was the Air Force Academy Cadet Chapel in Colorado Springs. We were commissioned to rebuild the envelope to a watertight condition with 1/32 inch tolerance. Conceptually, the original building was a brilliant piece of combinatorics, repeating parts, forming a greater whole. But when we started working on it, every instance was unique due to field conditions and change over time. So our strategy was simple. We started with 3D scanning the existing structural steel modeled tailor-fit parts in CATIA, and then generated cut files and robotic workflows using Grasshopper and Rhino. And to manage that complexity, we embedded metadata all the way from CATIA and communicated that throughout the process to the robot, including embedded directives in the robot controller, that kind of, removing the paper directive there a little bit. But so this way, we were able to index the parts to the robot and back to the digital model. The key is we didn't try to automate everything. Welding, as I mentioned, is full of tacit knowledge, the pace of bead, the instinct to adjust. Instead of trying to automating everything, we focused on where automation made sense, so positioning and orientation. And that gave our union welders a precise starting point so they could do what they do best. In that way, we worked throughout this process side by side with them. I think some of the earlier sessions touch on that, like tool building for people, the users, so getting feedback from the users, in this case, the union welders, to kind of make the best process. In the end, the future isn't about replacing craft, it's about making it enduring, turning their expertise and experience into knowledge that we can build on. So next up is the field, with a project again where union craft and automation kind of comes together. But in this case, every scope kind of converges with SurveyLink. So it's the riskiest phase of a project, and most of you are familiar with that, not just because of kind of the tough working conditions, but even the smallest error can cascade into costly rebuilds or schedule delays, right? And the install crew feels that pressure the most, juggling fast-moving parts, often up until recently relying on like 2D directives, dimension tables, or checking manually. So our question was simple: how do we extend computation to the field? And the answer was SurveyLink, not to replace the craft, but removing the guesswork so crews can spend more time building and less time checking. SurveyLink is Zahner's proprietary in-house developed platform that kind of connects the design model to field instruments, giving precise position and orientation information to any stakeholder, really. So that means robotic total stations, 3D printed jigs for reflector prisms, and a kind of a cloud platform built in JavaScript to queue and track positions. So we scan the field condition, we get a point cloud, and then reconcile that with the design model, create a directing model that then feeds our web platform and the cloud calculators. SurveyLink has already been deployed on many projects. Air Force Academy Cadet Chapel is one of them. At the chapel, we draw roughly 6,000 anchors into place, which means rest of the scope just flies in. Currently, the crew is installing the very last bits of the hubs that we looked at with robot-assisted welding process. Here's another project, same kit of parts, very different geometries. But with this project, there was 1,600 unique kind of dual curved surfaces or very complex curvatures forming a continuous curved finished building. And here's the space shuttle, the Endeavour, being housed in the California Science Center. At exactly the same process, same kit of parts, again, different geometries. With this one, we draw roughly 350 outriggers into place, and resulting in ZEPs and skins flying into place without any issues. SurveyLink is a project-agnostic tool that help our field crew navigate complex layout processes. It turns feedback loops from days into minutes, with data accessible to everyone. Installers in a basket, managers in the office, or even some stakeholder checking in remotely. With every deployment, it leaves a digital trace, so we can start collecting that data, analyzing it, and identify pressure points earlier on, and start kind of making better judgment calls from earlier, both in the shop, field, and design. And because it's a node-based platform, we can connect other communication devices into the system, like the crawling robot we did with Maria Yablulina to access hard-to-reach places. But again, with this one, I think the future kind of points us towards not automating robots, but connecting the knowledge back into the life cycle itself. So far we looked at how robots, craftspeople, and computation form and shape and position geometry in shop and field. But some of these principles extend to the very surfaces of the metal itself. So we'll take a look at patinas. Patinas are living minerals that form on metal surfaces. They are both aesthetic and performative. They change with environmental stimuli, so like salinity, pollution, time, just to name a few there. And in nature, this is a very slow forming process. It's also a very unpredictable process, but beautifully complex. At Zahner, we learned to guide that process. Uh, for decades, we've been working with pre-weathered patinas, experimental, hand-applied, eventually deployed on major projects. But much of this work has been developed under the leadership of Bill Zahner. And so oftentimes he reminded the team that patinas need a controlled variation, too much control, and it's just like paint. So our patent pending process, selective patina, builds directly on this kind of legacy of the kind of control to the variation that Bill described. With selective patina, our designer tools extend into a new space where we can convert design intent into machine instructions. With selective patina, and my titles are funky, I just noticed that. With selective patina, designer tools become chemicals that accelerate or resist oxide growth. Or application typologies become a designer tool where you can just custom design your end effector, and all resulting in an offset cycle surface development in the environments that they live in. Another one is fluid dynamics. So spray heights can act as filters, high pass versus low pass, how the chemical spreads on the surface with motion control. Or time and sequence could become a design parameter. So we can start to layer chemicals to get certain colors or build towards a performance criteria. Or we can manipulate spray density at the computational level of droplets or overspray. Once you start designing with recipes, layering, motion control, this no longer becomes a design exercise of form, but rather process physics. In summary, selective patina makes finishing programmable, a CNC for chemistry. Programmable when we want it, and variable where we design it. With plug-and-play tools, we can start chaining devices, and start developing new processes in collaboration with design teams. And basically the design intent gets cross-referenced to like a future library, and then generates a G code or a machine code that runs in a CNC gantry or a robotic arm. But the exciting part about this process is that we have a parallel computing framework that listens to every line of code that's being executed in real time, and adjusting application settings. And as the machine runs, we're kind of starting to collect these IoT embedded devices to collect feedback from the application process, so it can become a system that learns from every surface that it makes. So it allows us to do repeatable things. But to understand patinas in the way that we want to start extending this design parameters into, environmental variables and such, we really need to dive deeper into understanding patinas with in the environments they exist in. So that's where computational patina comes in. And this is kind of a newer work that we've been diving into. Computational patinas is a data-driven ecosystem of tools that turn patina knowledge into programmable, predictive, and performative surfaces. There's 5 layers to this framework: data collection, data processing, data structuring, and then relational modeling, and finally the insight engine. So we started this journey with what we know, which is our 8 legacy patinas. We built a data collection system that we kind of take images of our patinas and their aging in the environments, So we also built up a environmental metrics collector sensor kind of a system. And then once the data is collected, it goes to the processing where it gets cleaned, structured, and classifiable. And we have 2 points of data collection in this case. One is in the lab using our accelerated weathering chamber, so we can start seeing cause and effect very quickly. And then the other one is out in the real world with our IoT field kits, so we can understand how they naturally actually change. And once we have this pipeline, we can start automating, collecting the data and analyzing it. Especially in this case, we're looking for color change in relationship to the environmental parameters. But again, just color change is not the deep understanding there. So we've started working with external laboratories to develop a pipeline to understand color change to mineral build correlation. And there's also a lot of other kind of data collection points at Zahner. So patina knowledge is not just how the patina ages, but it's that decades of generational knowledge that we have. So we're actively looking for new methods and technologies that might help us collect and kind of build upon. So we cleaned our data. It is ready to be structured. We structure it in an SQL database. And from there, it goes into our relational reasoning pipeline where we can use the tables that we created, like metals and chemicals, and start building the relationships between them. So for example, a chemical or a recipe uses chemical or a mineral forms on metal type of relationships. And this gives us that cause and effect understanding. And finally, this little command line looking kind of chat box is kind of our version of it, but we can start asking questions and get evidence-based answers like which patina performs best in zone B, zone A, or can you suggest a recipe for, if it's the parameters of the project are this. And the last insight engine is our kind of weather to stress cycle pipeline. So we started connecting all this testing data into real world weather data. So we can start understanding how patinas age in real conditions. Some of the additional work we want to do here is kind of make a more robust stress cycle calculator and prediction algorithms, and also incorporate historic Zahner projects, because that many years of history and projects aging in the real world, I'm sure there's a lot better understanding there that we need to tap into. And all of this work builds towards one goal, and it is not prediction, it's translation. It's a way to turn all of this knowledge into parameters that can inform design decisions. And I started with Zahner's story. From the beginning, Zahner's story has been about its people, kind of their craft, their ability to see possibility where others see limits. And with all of these efforts, we're trying to extend that into the design space so knowledge can become something more generative instead of static, and we can start connecting people who design to people who make and the materials that bring both to life. And lastly, if any of this resonated with you, we're actively looking for summer interns, potentially hiring, and also we are always looking for research collaborators. Thank you.